Welcome to the 12th lecture for Chemistry 312, Radiochemistry. This lecture is on the chemistry of uranium and its part in the nuclear fuel cycle. This lecture is in two parts. The readings for both parts are listed here. It's the reading on the uranium chapter in the chemistry of the actinides and transactinides, and it is linked to the web page. This lecture is going to focus on the chemistry of uranium in the fuel cycle. And the first part's going to evaluate solution chemistry, uranium separations, and then we're going to go to fluorination and enrichment. We're going to see that the solution chemistry of uranium is dominated by the uranium hexavalent oxidation state, which is UO2 2+. This compound, the uranyl ion, the oxygens are linear from each other, double bonded. And one of the other things we're going to see is that this uranyl species, this uranium-6, has a distinctive yellow color. Here's an example of uranyl nitrate. So it's UO2 with two nitrates associated with it. And it has this yellow color. Here's uranyl carbonate with ammonia. So ammonia uranyl carbonate. Again, the uranyl drives that yellow color. We're also going to see that this uranyl moiety is bound by the uranium 5F electrons interacting with the oxygen S and P orbitals. We're going to describe that, and we'll use a molecular orbital to describe this bond and the resulting uranium UV visible spectroscopy of the uranium-6, the uranyl compound in solution. For separations, we're going to explore how routes can be used to separate uranium. This was originally derived from the separation of uranium from ore, and then the separation of uranium from other components of spent nuclear fuel. And then the final segment of this part of the lecture 12 is going to discuss fluorination and enrichment. We're going to see that a lot of the initial chemistry of uranium was driven by its nuclear properties, particularly the difference in the nuclear property between uranium-235 and uranium-238, where uranium-235 has a high fission cross-section for thermal neutrons, uranium-238 does not. So this drove for the idea of trying to enrich that uranium-235 isotope from the within the uranium-238 isotope. Again, we're going to see natural uranium has about 0.7% uranium-235, where in nuclear fuel it's closer to 3%. So obviously, somewhere along the way, an enrichment process occurs, and what we're going to see is that it exploits the formation of uranium hexafluoride. So the uranium-6 only with fluorine ligands. This compound is volatile. That gas phase species is then used to enrich the uranium based upon primarily mass differences, but also going to explore other techniques that are used. This lecture is going to leverage the fact that the speciation of uranium, the chemical form, can be varied, and it's important for controlling its behavior. As we see here, there's examples of different chemical species of uranium, and one of the things that's striking is the color differences. We've already mentioned that uranium-6 is this yellow color. Uranium-4, particularly with the fluorides, are these green colors. Uranium-4 UO2, so uranium-4 dioxide is this brown color. This mixed oxidation state oxide is black, and this is the metal, so obviously zero oxidation state metal compound has a different color. So these colors obviously mean that the UV visible spectroscopy of uranium compounds will differ. So the chemistry will understand how separations can be derived by variations in oxidation state. And we'll also discuss some aspects of the role of ionic radius in the chemistry of the uranium compounds, particularly when we talk about distances between uranium and ligands, and we'll show differences related to the distance between uranium and oxygen in uranyl, and uranium and fluorine in the uranium hexafluoride. The nuclear properties of uranium, particularly uranium-235 fission process, drove an understanding of the separation and speciation of uranium in a number of systems. As we discussed earlier about the fission process in previous lectures, fissile isotopes are required particularly for thermal neutrons. As we showed previously, uranium-233, uranium-235 are two uranium isotopes that undergo fission. Plutonium-239 also undergoes fission. In a reactor system, one needs a sufficient concentration and geometry, particularly of these isotopes, to achieve the fission process. And uranium, one of the natural isotopes, is 235, shown here, 0.7%. 233 can be made by the neutron capture of thorium-232, making thorium-233, which beta decays protactinium-233, beta decays uranium-233. And plutonium-239 is made by the neutron capture of uranium-238, creating uranium-239, beta decay to neptunium-239, and then to plutonium-239. In this way, these two isotopes, uranium-233 and plutonium-239, can be created in a neutron flux. For the natural amount of uranium-235 in nature, for purposes of a reactor, one would like to enrich the amount of uranium-235 in the material that goes into the reactor compared to what's found in nature. And as we see here from our fission cross-section, here we have some data that's plotted for the fission of uranium isotopes, the cross-section plotted against neutron energy. And as we see for the 235, we have fission at thermal neutron energies, and for 238, we do not have fission at thermal energies. So this means if we're going to have a thermal reactor, we're going to need to enrich the amount of 235 in the material compared to the environment. In the environment, we have under 1% of uranium is in the 235. In nuclear fuel, it's over 3%. So we'll discuss how one does this enrichment, and it does drive the chemistry or the chemical investigation, understanding the chemistry of uranium. In a reactor, as we discussed in fission, there's lots of heat that's produced. We get about 200 MeV of energy per fission. That heat is then transferred to a coolant. That fluid is used to turn a turbine, and then that's used to produce electricity. And also, as we discussed in fission, we showed that the process was identified in 1937 by Hans Strassmann and Meitner, that we get this 200 MeV per fission event. Compared that to alpha decay, which may go up to 10 MeV, or beta, which is just a couple MeV. And we also get 2.5 neutrons on average produced for a fission of uranium-235. This means that we can develop a sustainable chain reaction when we have a fission process where one of the neutrons can come off and then fission another uranium isotope. The nuclear properties of uranium have really driven the chemistry for the fuel cycle. Here's an overview of basic chemistry of uranium for the fuel cycle, everything from removing the uranium from the ore, both separations to the formation of U3O8, then taking that material, converting it to other forms of uranium, such as uranium dioxide, uranium tetrafluoride, which gets converted to the hexafluoride for enrichment, and then uranium metal, which is also potential fuel. This lecture we're going to explore the fundamental chemistry of uranium and use that information for understanding the applications of uranium chemistry to the nuclear fuel cycle. Once uranium is enriched, it can be pressed into pellets, primarily UO2, in existing commercial nuclear reactors. These are pressed into pellets as you did in one of the laboratories. Those pellets are then inserted into tubes, those tubes into assemblies, and then these assemblies get placed together inside of a reactor. Other species of uranium can be used for fuel, such as nitrides, carbides, metals, and also other actinides. Plutonium, which is fissile, and thorium, the 232 isotope, capturing neutron, creates thorium-233, decaying to uranium-233 through protactinium-233. The chemistry of uranium is complex and interesting due to its multiple oxidation states. Great examples are shown here of different oxidation states and different compounds of uranium resulting in different colors. And we observed these in one of the laboratories. The chemistry of uranium will be exploited for understanding separations in solution and also utilizing in enrichment, making a volatile form of uranium. Also separation of uranium from the ore and separation of the isotopes we'll also explore through a non-chemical process, primarily physical processes involving diffusion, gas centrifuges, and lasers. In the environment, there are over 200 minerals that contain uranium. The bulk of these are oxidized uranium, and reduced forms as oxides, phosphates, or silicates have also been identified. Their classifications are based upon the coordination polyhedra of the crystals that make up these mineral phases. An example of an interesting mineral phase is here is pyrochlore, which has an ABO structure. And what's interesting about pyrochlore is that pyrochlores containing uranium are found in the environment. They've also contain lanthanides, so often lanthanide materials will contain uranium and thorium. And these materials are also potential host forms for radioactive waste, since you see here that they can contain a number of metal ions, including the actinides and fission products. Some of the basic uranium solution chemistry is presented here. In solution, uranium is a strong Lewis acid. It's a hard electron acceptor, so it forms strong complexes with the fluorides in the halide group and weaker complexes with the iodides. We see the same trend in the oxygen and nitrogen groups. The hydrolysis behavior, the tetravalent uranium species hydrolyzed to the greatest extent and the pentavalent to the least extent. Overall, in solution, uranium-3 and uranium-5 have very little data. Similarities are drawn from the lanthanides or pentavalent actinides such as neptunium. Uranium-6, as the uranyl, which we'll discuss, is the most stable oxidation state in solution. Uranium-5 and uranium-4 can also be in solution, but uranium-5 is very prone to disproportionation, in other words, oxidizing to uranium-6 and reducing to uranium-4. Now, the relative stability of some of these compounds can be changed based upon pH and complexation to ligands, and we'll explore that in a little bit. The main driver of this chemistry and why uranium has these, in the 6 has these uranyl behavior, has to do with the 5f electrons, and we'll demonstrate that with molecular orbitals. Looking into more detail on the oxidation states of uranium, we see that the trivalent and tetravalent uranium species are mainly related to synthetic organometallic compounds, non-aqueous solutions. And here's an example of an EH diagram where the potential and the concentration of species are shown. And what's demonstrated here, this line shows the stability of water. So under these conditions, the solutions are, the compounds in this side are stable, compounds on this side are not stable. So we see that uranium-3 is on the unstable side of this line, whereas uranium-4, 5 listed here, that, by the way, that should be a plus, not a minus, and 6 can be found in solution. The other thing we want to point out is by changing the solution concentrations, in this case if we look at something very basic with a lot of carbonate, we see that uranium-5, shown here, is stabilized to a greater extent through the formation of this carbonate species. So by changing the ligand conditions, we can change the speciation of the system and stabilize different oxidation states. Now, uranium-5 and uranium-6 compounds have what are called these eel oxygens, where you get a uranium double bond to an oxygen, relatively short distances, and this characteristic plays an important role in the chemistry of uranium. An overview of uranium solution chemistry as a function of oxidation state is provided here. Uranium-3, as we showed with the EH diagram, is not stable in aqueous solutions, and there are very few studies of uranium-3 in solution due to this lack of stability. There's no direct structural information on uranium-3. However, comparisons with trivalent actinides and lanthanides can be used to lend information on the expected structure of uranium-3 compounds. Tetravalent uranium is stable in very strong acid, and the strong acid is required to prevent hydrolysis. You can prepare tetravalent uranium from uranium-6, where you can perform electrolysis on systems, reduce uranium-6 to uranium-4, and have complexes in the solution which will help stabilize the resulting uranium-4 species. Like other actinides, uranium-4 has a large number of coordination sites. Coordination number of 9 is expected. Pentavalent uranium has a very extremely narrow range of existence. We did see an example that in the aqueous phase it has uncomplexed, very low concentrations, but with certain systems, such as the carbonate system, it can be stabilized. Uranium-5 has been, these stabilizations have been used to prevent rapid oxidation or reduction or disproportionation, and be useful in evaluating information about the expected behavior and structure of uranium-5 compounds. The redox potentials gives free energy and other thermodynamic data for the different uranium oxidation states is presented here. Uranium-6, hexavalent uranium, is the most common uranium oxidation state in solution. And from solution species, a large number of compounds have been prepared, either by crystallization or hydrothermal methods. And the main species of uranium-6 in solution is the uranyl. Here's an example of water coordinating to uranyl. There's uranium, oxygen, here's the waters, and we see that this axial coordination is dominated by the oxygens, which we'll describe through the F electron interactions. And this equatorial plane is where ligand interactions can occur. We see the waters coordinating with the uraniums through this equatorial plane. Data for the hydrolysis of uranium-6, uranium-4 species, and estimates of uranium-5 and 3 are provided here. So this allows us to use this data to do speciation calculations. As we've already mentioned, the chemical bonding of uranium in solution is dominated by the uranyl, UO2 2+ species. This linear molecule is derived from the interactions of the 5F electrons and the 2p and s orbitals on oxygen. Modeling has been performed to look at those interactions of the atomic orbitals to form the molecular orbitals. And here's some data from both the ionic and density functional theory results. The molecular orbital is shown in more detail here, where here are the orbitals from the uranium atom, the 6d 5F, and the oxygen atoms shown here. There's 2 oxygen atoms. What is demonstrated here in this molecular orbital is the highest occupied molecular orbital is composed of these sigma and pi bonds shown here. These sigma and pi bonds can be excited through absorption spectroscopy to occupy these levels. And this is what gives rise to the characteristic absorption spectra for uranyl that we've seen in the lab. And here's an example of data in uranium-6, the uranyl ion, in nitric acid from 0.1 to 8 molar. We see the very characteristic peak with some changes due to change in speciation as a function of nitrate concentration. Now, the reason that these orbitals exist, that these molecular orbitals exist, is the mixing of the atomic orbitals. An example is shown here. Here's the p orbitals, the pz squared, 2pz orbitals from oxygen, mixing with the 5FZ cubed orbital from uranium, forming these sigma orbitals. As we can see, not only can these sigma orbitals form, but some pi orbitals, the sigma, and another pi orbital, and here's a sigma orbital. So those are the 4 orbitals, 2 sigmas, 2 pi's, that are responsible for this eel oxygen coordination in uranium-6. Has to do with this pi, this pi, this pi orbital interacting with these f orbitals, this s interacting with this s f orbital, and the other f orbitals are non-bonding. As we've already stated, the uranyl is UO22+. So these eel oxygens force a formal charge on uranium, which is below its 6 oxidation state. Now the net charge on the metal ion is actually a little bit larger than the 2+, estimated to be around between 2.4 for the water system and 3.2 for the fluoride system. And since the overall charge of this is +2, that means that the oxygens are going to have net negative charges on them. This has been exploited for forming metal complexes with these eel oxygens. These are called cation-cation interactions that you can explore for the actinides. And these can be evaluated by assessing the change of the uranium-oxygen bond through the complexation, and this bond can be evaluated through IR and Raman spectrum. As we mentioned earlier, the thermodynamic data for the uranyl species are available. In a very simple system, with the total amount of uranium being 1 × 10⁻⁶ moles per liter, we see that above pH 4, the free uranium begins to disappear. Around neutral, it gets dominated, the speciation is dominated by the dihydroxide. And at higher pH, we get the trihydroxide anion formed. If we go to higher concentrations, we see a notable difference where between pH 4.5 and up to around pH 11, we get schopite, which is the hydroxide precipitate of uranium dominating at higher uranium concentrations. These speciation calculations were performed with CHES, which was explained in the speciation section of the radiochemistry course. The uranium chemistry we've just described can be used for separating uranium from ores and making compounds of use to the fuel cycle. So we'll explore this, and we'll start off with the obvious location, separating uranium from ore. The initial separation or concentration of the ore is just based upon density. Then once you have a phase of ore with a relatively high concentration of uranium, the uranium can be leached into an aqueous phase. Once in an aqueous phase, the uranium can be removed from other metal ions by ion exchange, solvent extraction, or precipitation. There are 2 main routes of separating the uranium from the ore. One is an acid leach, so sulfuric acid, pH 1.5. You form the uranyl sulfate species. They're anionic in nature. They can be separated by anion exchange. Oxidizing may be necessary, so some oxidizing agents are used. And if iron is present in the ore, it can be removed by precipitation close to pH 4. If you're in a system such as limestone, which has a lot of capacity to absorb acid, one can explore carbonate leaching. With carbonate solutions, one can form the anionic uranyl carbonate listed here. Under these conditions, most other metal ions will be precipitated, so you can achieve a relatively rapid separation of uranium in the solution phase, other metal ions in the solid phase. Use of bicarbonates prevents the precipitation of the sodium diuranate, and this is primarily used for gypsum and limestone in the host aquifers, since adding acid would dissolve these host forms preferentially. Once in solution, the uranium forms can be recovered through anion exchange, solvent extraction, or chemical precipitation. An example of anion exchange is listed here, where both these cations of the carbonate or sulfate species can be loaded onto an anion exchange resin and then eluted with either weak acid, or a salt solution. In the solvent extraction system, which we'll describe in a little bit more detail coming up, it's similar to the tributyl phosphate system that was explored in one of the labs. You can have a continuous process. However, the solvent extraction is not well suited to the carbonate system, so it's better suited to the acidic sulfate system. Chemical precipitation. One can precipitate the uranium out by the addition of a base, peroxides, or ultimately the formation of the ammonia diuranate, the yellow cake, which is shown here. And then heating most of the precipitated chemical forms results in the U3O8 or even UO3, depending upon the level of oxygen and temperature in which the heating is performed. Here's an example of uranium purification by solvent extraction, similar to the tributyl phosphate extraction that was done in the laboratory. Except in this system, a pulse column is used. These columns, for instance, we would have a feed tank that would hold the solution containing the uranium, a column with tributyl phosphate. The aqueous phase would be added to the pulse column, migrate down. As that drop moves down the column, it will exchange, it will form the uranyl nitrate tributyl phosphate species, which then gets extracted into the column. The aqueous phase going here, the organic phase containing the uranium here. The organic phase is taken, added to this scrub column. So this could be the same concentration of acid, so let's say 3.5 molar. As the organic bubbles float up, any metal ions that aren't the uranium can be preferentially removed. The uranium preferentially stays in the organic phase. This organic phase is then transported to a strip column. This contains a lower acid concentration. The tributyl phosphate moves up and leaves behind the uranium in the aqueous phase, in which the uranium can then be collected and formed into uranyl nitrate. Right, so we went over how to separate uranium from the ores and how to purify the uranium from those ores. Now we have a system where we need to enrich our uranium. If you remember, natural uranium is only 0.7% 235. Depending upon what the needs are, for instance, a light water reactor, where we need 3.5% enriched uranium 235, or for a submarine reactor, over 90% enrichment, the process is going to need to be used that takes that uranium from 0.7% uranium 235 to the desired percentage of uranium 235. And here's some data on uranium enrichment related to devices. 10% cannot be used for a device, and 20% needs around 100 kilograms, and this is the boundary for high enriched and low enriched uranium. In order to achieve a separation of uranium isotopes, methods other than chemical separations are going to need to be exploited. The differences in the isotopes can be primarily mass, or perhaps even the nuclear magnetic moment, thinking about the difference between uranium-235 with a different spin and parity than uranium-238. Mass-based separation utilize uranium hexafluoride. Uranium hexafluoride is volatile. As we can see here from the phase diagram, it has a large gas phase component. And this uranium hexafluoride can be formed from the reaction of uranium compounds with fluorine at elevated temperature. This material, the uranium hexafluoride, has a density of about 5 grams per liter. It sublimes in normal atmosphere, going from the gas to the solid, and has a vapor pressure of 100 torr, or 1 atmosphere at 56 degrees. So if we took this material, heated it to 56 degrees, we'd have an atmosphere pressure of uranium hexafluoride above it. The molecule has OH symmetry with uranium-fluorine bond distances of about 2 angstroms. The structure of the molecule is provided here. Very simple OH symmetry. The material has very low viscosity, as shown here. It's on the order of water. This is a useful property for enrichment. And with water, uranium hexafluoride reacts to form the uranium dioxy difluoride and HF. Uranium hexafluoride, as you can imagine, with a fluorine compound, can react with a number of metals, however is found not to react with nickel, copper, or aluminum. So materials made from these elements are needed for the enrichment process. We'll explore some routes that exploit this volatile behavior of uranium hexafluoride for enrichment. The first example of enrichment is a rather straightforward system relying upon electromagnetic separation. Fundamentally, this is what's used in a mass spec. Ions are accelerated in a potential. They have the same kinetic energy. If they have the same energy, if their masses are different, their velocities will be different. If these ions are in a magnetic field, they'll have a radius listed here. This radius is a function of mass, velocity, the charge, and the magnetic field. So we can see that the radius is equal to those components shown here. And it turns out that the radius of an ion is proportional to the square root of its mass. So we have a way of achieving a separation. Ions of different masses will have different radii if we put them into this system. The higher the mass, the larger the radius. So this is what's exploited in electromagnetic separations. The other components that are necessary are relatively low beam intensities. High beam intensities have high beam spreading. So for achieving the separation based upon the change in the radius, see the radius is a function of mass. If we have high beam spreading, the spreading can be on the order of the differences in the radii, limiting the ability to have separation. During the Manhattan Project, calutrons were developed to exploit this fundamental property in separations. These calutrons were developed by Ernest Lawrence based upon the cyclotron. It's the California University tron. They have high energy uses. In Iraq, they were developing calutrons, and they required a great deal of energy. During the Manhattan Project, the calutrons shown here, there were two, an alpha and a beta. Here's an example of the calutron. Here's a schematic of the calutron. And fundamentally, you can think of this as an NMR where you would need to shim these magnets. As long as the magnets are kept in the right field, the magnetic field achieves the separation of the different masses. So this can be achieved by looking at the path that would be taken by the heavier isotope, which is shown here, and the lighter isotope, which is shown here. So obviously, if we were injecting uranium into this system, the uranium-235 would collect here, and the uranium-238 would collect here. As long as the magnetic field was constant, the different uranium isotopes would land in these different spots. While the calutrons were sufficient for use in the Manhattan Project, their efficiency was not suitable for industrial applications for the nuclear fuel cycle. The first method that was developed was gaseous diffusion. As you can see, by the late 70s, most of the world's uranium was enriched through gaseous diffusion. Later, this was overtaken by gas centrifuges, which we'll explain next. Gaseous diffusion is based upon thermal equilibrium. So if all molecules in a gas mixture had the same average kinetic energy. So these average kinetic energies are the same, 1/2 mv squared, are the same if the average kinetic energy is the same. The one with the isotope with the lighter mass will have a higher velocity. On average, uranium-235 hexafluoride is about 0.4% faster on average than uranium-238 hexafluoride. If we put this in a system where it impinges upon a barrier, and this barrier has a certain permeability for the uranium hexafluoride, the uranium-235 hexafluoride will impinge upon that barrier more often and diffuse through, on average, at a higher rate. Now, uranium hexachloride can also be used for enrichment. But the question is, why would this be more complicated? And that has to do with the fact that the chlorine has 2 stable isotopes, so your masses would vary based upon not only the uranium but also the chlorine. So the uranium-235 hexachloride, being lighter, would impact the barrier more often and have a higher probability of diffusing through that barrier. The barrier properties, like what we'd mentioned earlier, needs to be resistant to the hexafluoride. This includes the use of nickel or aluminum oxide. Also some engineering parameters. This hole in the barrier, the diameter needs to be smaller than the mean free path so that the prevents gas collision within the barriers so that the uranium wouldn't be diffusing back out. And it needs to permit permeability at low gas pressure, so you need very thin material. There's a few types of materials that have been examined. A film type with pores created in a non-porous membrane. This can be done by dissolution or etching, or an aggregate barrier where the pores are voids between particles in sintered barrier. Often the material is a composite barrier from films and aggregates. An example of a gaseous diffusion system is shown here. The uranium hexafluoride would be introduced in this stream, travel along this tube, contact the barrier, where after contacting the barrier sufficient times, permeate through the barrier. Some of the controls of this include heaters, coolers, and compressors to control the gas. Most of the time they operate at above 70 degrees and pressures below 1/2 atmosphere. You can quantify the behavior of an enrichment cell by this factor being the R of the product and the R of the tail, where R is the relative isotopic abundance, the number of 235 divided by the number of 238 atoms. From an ideal barrier, we would have something where the product and the tail, so this would be the tail, what makes it through the diffusion barrier, and the product, what comes on the other side. The product would be equal to the R of the tail times 352 divided by 349. That's the mass of the hexafluoride for the 238 and 235 respectively, and the square root of that, since we're talking related to the kinetic energy, and it's the square root of the velocity. The ideal system would have a Q of 1.00429, very small value for enrichment. This Q that we discussed in the previous slide is an idealized value under the best conditions. The real barrier efficiency is not nearly as good. It's actually around 70% of this amount. This can be influenced by a number of conditions, including pressure, mean free path of the system. An increase in temperature leads to an increase in velocity, and this can also increase the uranium hexafluoride reactivity. So the uranium hexafluoride does react with the system, and obviously increasing the temperature leads to that. Normal operations, about 50% of the feed diffuses, and in order to optimize separation, one has developed cascades. And these cascades are linked together and are used in tandem to. Here's an example of a cascade where uranium will come in, the product will be fed to another, and then another, and then another, and then another. And as you can imagine, if we had this very simple cascade, a good deal of the gas does not go through the enrichment process, so it winds up being a very wasteful process. Another route are countercurrent, both symmetric and asymmetric countercurrents, where product goes through and the resulting tails get refed into the system. So your feed is moved around straight through where the tails can be reintroduced. The cells in this case tend to be bundled together, and we get a decrease in cells at higher enrichment. For these processes, the number of cells in each stage have to be balanced with the tails in the product. Stages can be added to achieve changes in tailings depletions. So you can vary the overall enrichment by changing stages, which are composites of cells. A unit that's used to evaluate the relative energy for enrichment is called the separative work unit. And it's the energy expended as a function of amount of uranium processed and enriched to a degree per kilogram. So for instance, if I want to get to 3% uranium-235, if I have tails that are 0.25%, I would need 3.8 separative work units. If I have lower enrichment, I would need larger separative work units. The equation for separative work unit is listed here, and it's a function of the product mass, the waste mass, the feedstock mass, and the isotopic fractions. The gas centrifuge is what's commonly used today and has surpassed the gaseous diffusion method as a way for enriching uranium. The gas centrifuge is just what it sounds, a system that will push heavier. If it was a liquid system, the more dense would go against the wall, and the center would have the lighter component. In this case, against the wall, as it's enriched in uranium-238, and the center has more uranium-235. The density is related to the uranium hexafluoride pressure. The density minimum is at the center, and you can actually look at the density as a function of the radius with this equation, where the terms include molecular mass, the radius, and the angular velocity, so fundamentally how fast the centrifuge moves. With different isotopes, you can solve this density for each isotope. We can use this fundamental equation to evaluate the efficiency of gas centrifuge systems. So what we can see here, the partial pressure of a heavier isotope is greater at the walls and less in the center. The light isotope is greater in the center. So if we had a system where we can bring a gas into the centrifuge, spin the centrifuge, collect from the center, we would preferentially be collecting the lighter isotope. Now compared to this stage separation Q that we looked at for the diffusion system of 1.004, for a gas centrifuge is much higher. For a system of a 10 centimeter radius and for a frequency of 100 hertz for uranium hexafluoride, Q is 1.26. So this Q is increased greatly by using the gas centrifuge. While the gas centrifuge system has this high separation factor, it's much more complicated than the diffusion setup. This has to do with the moving parts involved in the centrifuge. You have large acceleration pressures, and The fact that these centrifuges are moving at high speeds require finely balanced centrifuges. And you also have to design them so resonance frequencies are limited, so when they begin to spin, vibrations do not occur. And these high speed induces stresses on the materials that weren't necessarily found in the gaseous diffusion system. So again, alloys of aluminum or titanium and certain composites are also explored and used in the gas centrifuge system. And some of these composites can include non-metallic features. So here's an example of a gas centrifuge where we can feed gas in. It's spun. We get the diffusion concentration of the heavier gas on the outside, lighter gas on the inside. The light fraction can be taken out through the center. The products are removed by a top scoop. The tails are removed by a bottom scoop, with the feed being introduced into the center. So this is superior stage enrichment compared to gaseous diffusion, and it needs fundamentally less power to achieve higher separations. So a 1,000 megawatt electric reactor needs 120,000 SWUs, separative work units, per year. In a gas diffusion, you get on the order of 9,000 megajoules per SWU, where the centrifuge is only around 200 megajoules per SWU. And here's an example of a cascade system of gaseous centrifuges, where we would take the gas, feed it into the center, remove the light and the heavy fraction, then feed that into the next centrifuge. An advanced separation that's under exploration is laser isotope separation. In this, you're actually looking at atomic differences between uranium-235 and uranium-238 to achieve separation. These differences are often observed in the visible part of the spectra, but they're relatively small. The energy differences between the atomic electrons in the different isotopes is small, generally so small that it's not generally achievable. However, with lasers, one can tune to the exact transition species and produce a molecule of a given isotope in an excited state. There's 3 classes of laser isotope separation: photochemical, atomic photoionization, and photodissociation. The photochemical, it's a reaction of an excited state of the molecule, so that the molecule that's preferentially excited, that isotope will have a different state, different excited state that can be reacted. With atomic photoionization, the isotope that's targeted will be ionized, so then it can be separated. Or they can undergo photodissociation, where instead of being uranium hexafluoride, it can be transformed to uranium pentafluoride. There's 2 examples: AVLIS, which is an atomic vapor laser isotope separation, and MLIS, the molecular laser isotope separation. And we'll explore these methods. AVLIS uses a uranium metal vapor, so it's produced by an electron beam, and you take this uranium metal vapor and it goes into a gas phase, and you have multiple ionization steps. Uranium-238 has an absorption peak at 502.74 nanometers, and the 235 is 502.73. So what one can do is multiply ionize the uranium-235 preferentially, first by hitting this 502.73, make an excited state, and then take that excited state, ionize it, and then the uranium that's ionized is deflected by a magnetic field, thereby enriching the uranium-235, and like the other systems, one would need a cascade. Molecular dissociation is also used as a laser-based isotope separation method. Similar to what we talked about with the metal, one can use the hexafluoride you can initially excite the uranium-235 hexafluoride with IR excitation. In that excited state, you can selectively take this excited state to the ionization state, where uranium hexafluoride is converted to uranium pentafluoride. The uranium pentafluoride is not a gas phase molecule. It precipitates out as a white solid. This white solid can be collected. It's preferentially enriched in uranium-235. It can be converted back into the hexafluoride and fed into another excitation system. Again, a process that needs cascades for the overall enrichment. Okay, this concludes the first part of the lecture on uranium and the nuclear fuel cycle. This concludes the first part of Lecture 12 for Chemistry 312, Radiochemistry. This lecture reviewed solution chemistry of uranium, some uranium separation methods, and how uranium is enriched through the formation of the uranium hexafluoride species. The second part of Lecture 12 will discuss the metallic state of uranium.